Good evening. We are into our last topic in that chapter, laws of motion. And our discussion for today is motion of a car on a circular track. The initial introduction to circular motion we already had in the previous chapter, motion in a plane. We're continuing on that discussion. And here we have two cases where both of them you will see are circular tracks in which a car is moving. The difference is that this is a level road and this is a banked road. What is a banked road? I'll explain when we reach into that topic. So we'll first take the case of a car moving on a circular track. This is a circular track of radius r, but this is a level road. Okay, now if I redraw this here, you will see this is our car, the wheels of the car. This is moving on a level road and this is taking a circular turn, and the circular turn has a radius r. Let us think about uniform circular motion, which we discussed in the last chapter. We said whenever there is a circular motion, then there is a centripetal force and therefore a centripetal acceleration. The centripetal acceleration, if you remember, is AC, which is equal to v square by r, and we also have that omega square r, where this v is the linear velocity in meter per second, r is the radius of that circular turn. This acceleration is always towards the center, and that is why it is called centripetal acceleration, center seeking. Because of this, we have a centripetal force given by F is equal to mass into acceleration. So this will be mv square by r. So this was introduced to you in the previous chapter. Now this centripetal force which acts towards the center of the circular path is, let's say in our case where we have a stone tied to a string and we are whirling it in a circular motion, then the tension in the string which acts towards the point of support provides you this centripetal force. If you cut the string, then the stone will fly off along the tangent, because we learned already that in a circular path, at any point, the velocity is always directed towards along the tangent like this, and the force is always a center seeking force, which we call as the centripetal force. So if you cut off the string at some point here, the stone must fly along the tangent. Similarly, if you look at the planets which go around the sun, the gravitational pull of the sun on the planet provides the centripetal force towards the center. Similarly, if you have a bike, if you're on a bike or a car and you're taking a circular turn, then the friction between the tire and the road provides the centripetal force. That is why if you're traveling if you're taking a circular turn, let's say it's rainy or your tires are old and there's not enough friction between the tire and the road, then what happens is you can actually skid along the tangent and have an accident, because you can't keep yourself on the circular turn unless and until there is friction providing the centripetal force which acts towards the center. So here what we have discussed is that there is a centripetal force provided by the friction between the tire and the road, which acts towards the center of that track. So for frictional force being a contact force between the tire and the road towards the center of the track, that is the frictional force that is acting on the car. The weight of the car will act downwards, mg, and you will also have a normal reaction which we know will be opposite to the weight. We already discussed this in previous sessions. We have the weight of the car acting in the downward direction. The road gives a reaction in the upward direction, which is what you call as the normal reaction, and this N is equal to the weight of the car. Now, if I'm going to resolve these forces, see, this car does not have any vertical motion. It does not move up or down, which tells you that this weight mg must be equal to the normal reaction. So, since the car does not have any vertical motion, I call this as my first equation. Then the centripetal force which we know is the mv square by r. So this mv square by r, the centripetal force, is provided by the frictional force, the static friction actually, because as you know, in circular motion, suppose a car is taking a, let's say, is traveling on a straight path and the driver suddenly decides to take a turn. Then, according to Newton's first law of motion, the body should continue in its straight path. So, even though the car has taken a turn, this body will now experience an outward force because it's trying to continue in its state of uniform motion. So, to keep this in motion along with this, you need to have a force of friction which opposes the relative motion of the car towards the because it's trying to move along the tangent, it will move away from the track, the center of the track. To keep it towards this force of friction must be the static friction which opposes the relative motion between the car, relative motion in this direction. So we have this static friction acting towards the center. So we may write this. You already know that static friction is equal to mu s n from our previous topic, because static friction depends on n, the normal reaction. It also depends on the coefficient of friction. What is this coefficient of friction? You know, it depends on the nature of the two surfaces in contact. If it's very smooth, then this mu s will be lesser. If it's rough, then the coefficient of friction is higher. So it depends on the nature of the two surfaces in contact. So we may write this is equal to Fs, which is equal to mu s n, which is our second equation. Now if I divide the second equation with the first equation, you have mv square by r into dividing by mg, that is 1 by mg is equal to, divide this and n gets cancelled, we have this as mu s. So I may cancel this m and I may write v square by rg equal to mu s, or v is equal to root of mu s r into g. Now you will see that this is the maximum permissible speed that this driver can take if it should stay on that circular path without skidding along the tangent. If he takes a speed greater than this, then the necessary centripetal force is not there, and therefore the car will fly along the tangent and have an accident. So you will see that this maximum permissible speed depends on g, of course, is a constant, 9.8 meter per second square. R is the radius of the circular track, and it depends on the coefficient of friction between the tire and the road. So to have higher speeds, you need to have large coefficient of friction, which means that tire and the road must be it must have a large friction. Large friction will definitely cause the wear and tear of your tire. So in order to have higher speeds without this mu s, meaning even if you have the coefficient of friction low, even if you have smooth surfaces, you can increase your speed by having what you call as the banked road. Now this banking of road, it means the outer edge of the road is raised with respect to the inner edge. So here we have the maximum speed V provided is mu s rg if it is a level road. Now let us look at this banking of roads. See, if this is the level road, suppose your track is a circular track like this, okay? Now on the circular track, if the outer edge of the road is raised through some height with respect to the inner edge. So if this is your circular track, this happens to be the inner edge. The inner edge is here and the outer edge is here for the road. This is the road I am talking about. If the outer edge is raised with respect to the inner edge, this is what you call as banking. You would have noticed this when you go on hairpin bends, when you go to hill stations. As you take the hairpin bend, you will notice that the outer edge of the road is slightly raised with respect to the inner edge, and that is what you call as banking of roads. So here I have shown you a circular track like this of radius r. Our car is still on this, but unlike this level road, you see that the outer edge of the road is raised at an angle theta with respect to the inner edge. Now if you look at the different forces acting on this, you will see that as usual, as expected, the weight of the car acts in the vertical direction, mg. The normal reaction I've told you is always perpendicular to the surface. So if this is a surface now of the road, the normal reaction will be perpendicular to this surface. Then the force of friction, which is a contact force between the tire and the road, provides the centripetal force, and that acts towards the center of the track, that is this circular track of radius r. So that's why our force of friction is in this direction. Let me redraw this and show you. So we have the outer edge raised. We have the outer edge raised with respect to the inner edge through an angle theta. Let me represent our car with just a dot. So we have this weight mg acting in the downward direction. Normal reaction perpendicular to the surface of the road. The force of friction towards the center of the path. This is the circular path towards the center of the path. These are the three forces that are acting on the car. Now let me resolve all these forces along the vertical and the horizontal direction. Now if this is theta, you know this is also going to be theta because they are alternate angles. Now since this is 90, this has to be 90 minus theta. Also, this is going to be 90, right? If this is 90 and this much is 90 minus theta, then obviously this has to be theta. So, you see, this is theta, this is also theta when this is theta. Now, if I'm going to resolve this n, this will be the adjacent component because this is theta. So, this is going to be n cos theta. And the opposite side to theta, this will be the n sin theta, which I'm going to mark here as n sin theta. Similarly, if I resolve this force of friction into the two components, this and this is theta, so this will be the adjacent component. So this is going to be f cos theta, and this is going to be f sin theta because the opposite side to theta. So I hope the diagram is clear to you. I have resolved n as n cos theta, which is the adjacent side, the opposite side, which is n sin theta. I have resolved this force of friction because this is theta, the adjacent component as f cos theta. The opposite component in the downward direction will be the f sin theta. Now, you will see that this car has no vertical motion up or down, which means you may write the mg plus the force sin theta, force of friction, which as you know is the static friction, is equal to n cos theta, or I may write mg is equal to n cos theta minus f sin theta. This fs as you know is mu s n. So I may write minus mu s n sin theta, which is the first equation. Then these two forces, components, that n sin theta and f cos theta, which is towards the center of the track, provides the centripetal force. So I may write mv square by r, that is the centripetal force, should be provided by the two components acting towards the center of the track, which is n sin theta plus, this is the static friction. So fs I will replace as mu s n cos theta. So we have our equation 2. Now if I divide equation 2 with 1, I will have mv square by r into 1 by mg equal to n sin theta plus mu s n cos theta divided by this n cos theta minus mu s n sin theta. Okay. Now I'll cancel m from here, so that now I have v square by rg equal to, I'm going to divide every term here with n cos theta. So on the right hand side, I will divide every term with the same value n cos theta. So that when I divide n sin theta by n cos theta, the n gets cancelled. sin theta by cos theta, I have tan theta plus mu s n cos theta divided by n cos theta, you are left with only mu s. So that is mu s divided by n cos theta by n cos theta, I have 1 minus, here n sin theta by n cos theta, n and n gets cancelled, you are left with mu s tan theta. Or you may write an expression for the V as the speed possible on a banked road. V will be given by V equal to, taking this Rg to the right hand side, Rg bracket tan theta plus mu s divided by 1 minus mu s tan theta and square root of that. So if you compare this speed with this speed, you will see that this Rg term is common, both cases, but this mu s has been replaced by this. Now mu s is actually mu s by 1, right? So when you replace this term with this, you will see that the numerator has increased by this tan theta. It was mu s, so now it's mu s plus tan theta. So the numerator has increased, denominator is 1, but the denominator has become even smaller, 1 minus mu s tan theta. So you see that this whole value is larger than mu s because the numerator has increased by tan theta, denominator has decreased by 1 minus mu s tan theta. This whole value is greater than mu s, which means by simply banking the road, that is raising the outer edge of the road with respect to the inner edge by an angle theta, you may have larger permissible speeds on that curved track. Then there's something called as the optimum speed, where you keep the wear and tear of your tires to minimum value. That is, you do not have friction at all. No friction would mean wear and tear of the tires are kept to a minimum level. So if you have mu s equal to 0, which is the optimum speed, where there is no wear and tear of your tires, you may write V equal to, so mu s is 0, then here also this mu s becomes 0. So this will be simply Rg tan theta, where theta is the angle through which your road has been banked, R is the radius of the circular track, and G is 9.8 meter per second square. So you see, you can have optimal speeds even without friction. You can take a turn with this speed. There will be necessary centripetal acceleration for you not to have an accident. And also you see that by banking a road, you can have larger permissible speeds on the curved track. So these were the two topics I needed to discuss with you today. One, the velocity or the speed of a car on a level road taking a circular turn, and the speed on a banked road, which is a circular track, speed which depends on the angle of banking. Thank you and good night.